Alright, today we're going to take a look at section 4.1, angles and angle measure. We've already looked at this in class, but I thought this would be a handy little review for after spring break. And let's start with the circle. So let's say that we've got a circle with a radius like so. Let me plug this in here. So we've got a radius like so, and another radius here, and an angle, theta. So this is length r, this length r. If it opens up an arc length, if it subtends an arc that's also length r, then we can say that the angle theta here, theta, is equal to 1 radian. So we get an angle of 1 radian when the arc length that is subtended is equal to the length of the radius. We also saw that if we take that angle and we bring it all the way around, we've done one full rotation, and that's equal to 2 pi. So the angle, if we go all the way around the circle, the entire circumference of the circle, kind of like if we took it in degrees and went all the way around the circle, it'd be 360 degrees. Well, in radians, we call that 2 pi radians. Now recall that if we're talking about the unit circle, this whole chapter, chapter 4, is about the unit circle and trigonometry, then r is actually equal to 1. So if we do a full circle, the circumference, if circumference we know is equal to 2 pi r, if r is 1, then that's like saying the circumference is equal to 2 pi, right? Because r is 1. So that's where we get this from. The angle in a circle, 360 degrees, is the same as saying 2 pi radians. So that's like saying that 360 degrees is equal to 2 pi radians. Now, most of the time we're not going to actually write out the radians. We're not going to write the word out, but that's what we mean. 2 pi radians. That's the unit of measure for the angle in this circular motion. We also saw that if we divide both of these sides by 2, we get 180 degrees is equal to pi radians. And then we use that to come up with a number of other measures, like 90 was equal to pi over 2, 45 was equal to pi over 4, etc. The common ones that we talked about were 30, 60, 45, 90, and then multiples of those. I'd encourage you to work them out, check them out in your textbook. You also have that in your notebook. We also talked about angles in standard position. Standard position. And that was where the terminal arm, the angle from the x-axis, from the positive x-axis, measured counterclockwise from the positive x-axis to the terminal arm. So this angle is in standard position. Angles in standard position have other angles with the same terminal arm that are called coterminal angles. If I took this angle here and went all the way around, it would be a different measure, but the terminal arm ends at the same spot. So if my first angle, for instance, was 60 degrees, then my second one would be an additional 360 degrees further along, or 420 degrees. These are coterminal angles. The terminal arm is in the same location. Anytime we measure an angle in a counterclockwise direction, it's going to be positive. So theta is positive. If we measure it in a clockwise direction, theta is negative. Okay, so if we go counterclockwise, it's positive. If we go clockwise, it's negative. And just to touch back on coterminal angles, we get coterminal angles by adding multiples of 360 Or in radians, let's say I had something like pi over 4, I would get coterminal angles by adding multiples of 2 pi. So I talk about adding multiples of 2 pi n. In fact, I could add or subtract multiples of 2 pi n if n was an element of the natural numbers, like 1 and 2 and 3 and 4. Okay, so adding 2 pi, adding 4 pi, adding 6 pi will give me coterminal angles, and likewise I can subtract. And I believe the last thing for section 4.1 was that when we talk about radians, it's especially useful for describing circular motion. So there's a relationship between the arc length, the radius, and an angle in radians. And that's to say that the arc length is equal to the angle theta times the radian. So if I have a circle, or let's say an xy axis here, and I have an angle here of, let's say, pi over 3, and a radius of 2, then my arc length is going to be equal to pi over 3 times 2, or 2 pi over 3. That's an exact form for the arc length, and of course I could plug that into my calculator as well and get, well, let's see, what would that be? That would be approximately 2.09 radians. Okay, I don't need to write the word radians, it's understood. Jumping to section 4.2, we talked about the unit circle. We continued with the unit circle, and we talked about the formula for a circle centered at the origin. And that was that x squared plus y squared was equal to r squared. So if I had a circle centered at the origin, and I had some point over here, let's call that point with point P with coordinates x comma y. If I plugged in whatever those x coordinates and y coordinates were, or the x value and the y value were, then that would equal, in this formula, it would be equal to the radius squared. So let's say that some point 4 comma 5 is on a circle centered at the origin. You could be asked to determine the radius of the circle. So if I use that formula, I can say that x squared plus y squared equals r squared. So that means 4 squared plus 5 squared is equal to r squared. Or 16 plus 25 is equal to r squared. I'm just going to jump over here. 16 and 25, that's 41, is equal to r squared. And when I take the square root of that, I get r is equal to positive or negative root 41. But of course the radius is a length, so I'm not going to get a negative value for that. I'm just going to get the positive root of 41. So the equation for that circle would be x squared plus y squared is equal to the radius squared, which is 41. For the unit circle, since the radius is 1, then the equation for the unit circle is x squared plus y squared is equal to 1 squared, which is just 1. Any point on the unit circle will satisfy this equation. When I take the x coordinate and the y coordinate and I square them and add them, I will get 1, if and only if that point is on the unit circle. Another thing to note about the unit circle, And remember from section 4.1, the arc length is equal to theta in radians times the radius. Well, if the radius is 1, then that means the arc length is equal to theta. So on the unit circle, the arc length, the length of that arc that's subtended by the angle, is the same as theta. Also in section 4.2, there were two triangles that we reviewed. In degrees, we talked about the 30, 60, 90 triangle, which had lengths of 1, 2, and root 3. And the other one was an isosceles right triangle with lengths of 1, 1, and root 2, and angles of 45, 45, and 90. In radians, we also talked about this. Each of these can be expressed in radians as pi over 3, pi over 6, pi over 4, and 90 as pi over 2. The lengths don't change, it's just the way that we write down the angle. Now, very important for some of the work that we'll be doing later, it's important to note that both of those triangles, those special triangles, can be made to fit inside the unit circle. So for example, I could be drawing this one out, where this is that 30, 60, 90 triangle. Remember, this was 1, 2, and root 3. But if we're talking about the unit circle, then we know that the radius here, the hypotenuse of the triangle, the radius has to be 1. So in order to make this 1, I divide everything by 2. And then I can go ahead and change that and say, well, now my radius is 1. I can also do it with that 45, 45 triangle. I can draw this out. I know this is at 1 and 1 and root 2, but if I want my radius to be 1, I have to divide both sides by root 2, and if I do that, not both sides, but all sides by root 2, and there are my, that's what my triangle looks like now, so that I've got a radius of 1. Doing that allows me to know the location of this point. The x-coordinate of point P, when I use the special triangle, is root 3 over 2, and the y-coordinate is 1 over 2. Likewise for this point P, the x-coordinate is 1 over root 2, and the y-coordinate is also 1 over root 2. If I take those and I plug them into the formula for a circle, remember that's x squared plus y squared equals 1, then I would have root 3 over 2 squared plus 1 over 2 squared, and that should equal 1. Well, root 3 squared is 3, and 2 squared is 4. 1 squared is 1, 2 squared is 4, and when I take 3/4 and add a quarter to it, I get 1. It works out. And the same thing here. 1 over root 2 squared plus 1 over root 2 squared should equal 1. 1 squared is 1, root 2 squared is 2. This is going to be exactly the same thing, and a half plus a half does equal 1. So we see that those points, we got to them easily using special triangles, are on the unit circle. Alright, so that's a quick review of the information that we covered, some of the information we covered in section 4.1 and 4.2. I'm going to do another video with some sample questions. You should watch both.